2.3a is types of discontinuities. All right, so first we have one that looks like this. Say it goes there. This is a whole / removable discontinuity. This is when you have 0 over 0 or your indeterminate form. This one right here, maybe it looks like this, and there's a point. Actually, yeah, sure, there's a point, and then it starts up there with a hole. There's another one that's similar, and this is where it looks like it's just a hole, but the value is actually up there. These are both called a step discontinuity. There's also this, where you have a vertical asymptote and the function does that. This is called an infinite discontinuity. So basically the limits, instead of being, a value that is the same or isn't on either side, it's just infinity. So here's another thing you should be able to recognize. Let's say you have a graph that goes up and goes down like this. That funny little point is called a cusp. And a cusp is a point on a graph that is continuous but has no slope / instantaneous rate of change. So for comparison, let's say you have a graph, looks like this, and there's a curve. If you were to draw the slope at this point and just like cut right through it, you could do that. By contrast, for a cusp, if you're looking for like where the slope is, it's kind of like a teeter-totter, like are you going up, are you going down? I don't know. So basically, there is no slope there. And if this doesn't make complete sense yet, or even much sense yet, don't worry about it. It will all become clear in future lessons. For now, if you know that funny looking thing is a cusp and there's no slope there, that's plenty. Keep in mind, a continuous function can be drawn without picking up your pencil. That's the most simple definition of a continuous function. Couple more things to talk about. First of all, how to remove a hole / removable discontinuity, because obviously if it's called removable, you kind of want to be able to remove it. Basically what you do is you write an extended function to better explain the graph. For example, let's say you have the function g of x equals x squared minus 9 over x minus 3. If we factor this, we get x plus 3, x minus 3 over x minus 3. And the x minus 3's cancel, meaning we can cancel out our whole at x equals 3. So graph-wise, this means whatever the function's doing anywhere else, let's say that's 3 and that's 6 and that's 3, whatever the function's doing anywhere else, we know that at 3, or when x is 3, there's a hole. And it looks like it should be 6. Because if you plug 3 in right here, you get 6. So the limit as x approaches 3 of g of x equals 3 plus 3, which is 6. The rest of the function, I don't really know or care what it's doing, but we know there's a hole there. So as far as our extended function, we essentially make it piecewise. So f of x equals, so that initial function, x squared minus 9 over x minus 3, is totally fine as long as x is not 3. When x is 3, you need to use the function x plus 3. Okay? So we keep it, we cancel out the whole, or we remove the whole by just using our simplified version when we were finding the limit. Last piece here is something called the continuity test. So a function is continuous if and only if. So this cool double arrow thing and IFF, which always just looks like a word spelled wrong, they just mean if and only if. Used in proofs and theorems and definitions and stuff. So a function is continuous, at C, if and only if, number 1, f of C exists. Number 2, the limit as x approaches C of f of x exists. And number 3, that f of C is equal to the limit as x approaches C of f of x. All 3 of those conditions must be true for a function to be continuous. So today we're going to be looking at this in terms of a graph. So let's look at, let's just make up a graph right here, okay? So let's say our function does this, there's a hole, and it curves up like that. There's a value right there. And let's say this is 5, this is 6, and this is 10. Okay, so looking at the continuity test, we look for these 3 steps. So first of all, does f of c exist? I'm sorry, we're checking at 5, so is this continuous at 5 is what we're looking for. So number 1, does f of 5 exist? Yeah, f of 5 is 10. What about the limit as x approaches 5? Well, the limit from the left, it's 6, and from the right, it's 6. So the limit as x approaches 5 is 6. So we're good so far. The function exists, and so does the limit. Number 3, we have to look at the function value and the limit, and they're not the same. So since f of 5 doesn't equal the limit as x approaches 5 of f of x, it's not continuous at 5.